But anyway, I'm going to be talking about the performance of the GBT telescope and the opportunities it enables for 3mm science. Oops. Whoops, I'm sorry. Whoops, there's a. So the optics, it's already been said, it's an off-axis design, and that provides a very clear aperture, low side lobes. And just to show some pictures, I mean, the telescope is big. We have a big subreflector here. You see the people working on it on the top. It's an 8-meter subreflector. You can observe in prime focus. We do that for low frequency by swinging out a boom. This boom here swings out in front of the subreflector. And then for Gregorian focus, it reflects off the subreflector down into the receiver cabin. And we have 8 receiver bays, so we can put 8 different instruments. So we have basically 8 holes, and you see the big feed here for L band and S band. But anyway, Argus isn't up here now, but Argus goes into one of these holes. As Karen mentioned, it moves over the entire sky, and we have a 5-degree elevation limit, so we can actually observe 85% of the entire celestial sphere. For its size, it actually slews pretty fast. Not fast enough necessarily to track, you know, satellites quickly, but fast enough to track astronomical objects. In terms of our ability to use it at high frequency, we have a dynamically scheduling system. Anybody who's observed with the GBT realizes you can be scheduled at any time. And it gets scheduled every day based on weather predictions. Even though we're out in the east, you might think we're pretty wet, but in our winter season, when we talk our winter season here, we're talking October through April, roughly 50% of the time during that winter season, historically, maybe things will change with climate change, but that's still an open question. But anyway, 50% of time has opacity. That's roughly acceptable for 3mm observations. And if you factor in the winds and the NSF 60% open proposal time, they're roughly around 300 hours of nighttime 3mm time that could be available for scheduling 3mm science on the telescope. Pedro will talk about lasting a little bit. That might expand that window into some of the daytime hours. What makes it work is the active surface. You could not maintain a 100-meter dish without an active surface. And especially, well, with the off-axis design, there's a lot of gravity sagging too that it has to correct for. So by moving these actuators that are in a circle there, we can maintain the accuracy of the dish to about 230 microns at nighttime. That on average, maybe 235. You can get down to 220 microns is about the best you can do right now. In terms of the history, and I should say this is, the work done on this has been done by observatory staff over 20 years, basically. I didn't even join the staff until 2009 after most of this work was done. But this just shows historically sort of how the telescope has improved. In 2009, they fixed the actuators or set the 0 points of the actuators, and that had a big jump in terms of the efficiency. Up here in the left is like, this is 43 gigahertz, that's Q-band efficiency, relative efficiency, and we use that to measure the gain curve of our telescope, which is just the response as a function of elevation. And in 2014, we improved our gravity Zernike model as a residual model that corrects for gravitational distortions, such that if you made a surface measurement at one elevation, now you can observe at another elevation and without a loss in efficiency. Before that, you would have some losses. You'd want to take your surface measurements, which we call OOFs. You'll see these things out of focus holography when we observe a bright source on the sky and then correct for the surface. Lastly, the Nixon, Pedro will talk about that in a couple of talks. It was with the scanner, and the idea there is to replace some of the time-expensive surface corrections with fast scanning with the scanner. But at Q-band now, these are relative efficiency. And if you take that over to 3mm, this would be effectively the aperture efficiency of the telescope of the GBT over time with the telescope. So you see, we've improved things quite a bit now, making 3mm observations possible. And if you invert this aperture efficiency, what it means in terms of surface areas, assuming the Roos equation, you get this bottom plot down here, and you can see the surface areas have gone down remarkably over the last 20 years. And Argus was not the first 3 millimeter instrument. We have Mustang, a continuum bolometer. We have a 4 millimeter, what we call the 4 millimeter instrument, which we use particularly mostly for VLB observations now. It was commissioned now, it's been 4 years. It hardly seems like 4 years, but it was commissioned in 2016, late of 2016. And as Karen already showed this, we achieved the theoretical beam with Argus, basically, which was very encouraging. The beam size roughly goes with 1.2 lambda D. This just shows observations. This is a result of observations of many people's science projects. It's all the way across the 4 millimeter band and Argus band from basically 70 gigahertz all the way to 115 gigahertz. And if you look at the calibration results, this is again over, gosh, it's hundreds of observations I took to produce this. And this is in a GBT memo that was published a year or so ago. And what we have here in the solid line is basically assuming the Roos equation with 235 micron error, and the data points show the measured aperture efficiencies derived from quasars, and then the squares are the main beam efficiencies for the point sources, and that scales with aperture efficiency roughly 1.3 times the main beam. The small source to main beam efficiency scales with 1.3 times the aperture efficiency roughly, which is consistent with the beam size. If you observe brighter sources, you measure a higher main beam effective efficiency. You're just instead of a point source, and this shows the results of Jupiter at the top versus quasar. So a lot of galactic science using extended sources. You could argue you want to use a Jupiter efficiency, or if ideally maybe you could observe Mars. So here's a table of the results. I won't go through all of it except to mention, if you look at something bigger, you get a higher effective beam efficiency or observed beam efficiency. For Jupiter's 53%, the moon's like 80%. There's roughly 95% of all the light that GBT will see within 1 degree of where you point on the sky, roughly, if you multiply these two numbers together, which is quite remarkable. That's what you get from having an off-axis design. Very little spillover, and your forward efficiencies are quite high. In terms of just general performance, of the GBT, blind pointing. If you point on just a random part of the sky, your error is of order 10 arc seconds, which is much bigger than your 3 millimeter beam. If you do offset pointing, you point somewhere on the sky and you move the telescope some random other place on the sky, you're just about 4 arc seconds away. If you point nearby your source, like certainly within 10 degrees or so, then our offset pointing based with our models is roughly about 1 arc second. We track roughly to probably a little better than 0.5 arc seconds. We need to measure this. We replaced the servo system about 2012, 2013, and the servo errors used to add almost an arc second, and the actual servo motors now are only adding about 0.2 arc second error as measured in the lab. We still need to confirm that on the sky. And then in terms of our surface corrections, typically what we do at nighttime at 3 millimeters, we observe with the OOF observations, that holography, you observe a quasar in focus and out of focus, and you back out what the surface would need to be to make a point source, and you can get about 230 microns. If you don't do an OOF correction, and as long as it's not super, super cold, the gravity Zernike model works pretty well. It's for more typical conditions. You can get anywhere from 250 to 300 microns, even without an OOF. During the day, it can go up a lot, 350, 400 microns. And if you don't use our active surface in all the models at all, then you're talking almost like a half a millimeter in terms of our surface air. Potentially our limiting factor now we've improved the surface over the last 5 years. And lastly, we'll improve things even more. I think in the next area of work that we should probably look at is improving our pointing model on the GBT. And this is something when you're doing mapping experiments to keep in mind that you might want to register if you take maps at different times. And if you have bright sources in there, you want to maybe register subsets of your data to line them up. The pointing model is relatively pretty good if you're going all sky at lower frequency. The square over here, if you're all over the sky, if you just randomly look at pairs of pointing observations taken over like an 8-hour run all over the sky, you're within 4 arc seconds, which is very good. And what this shows here is the offset pointing as a function of distance. But so 4 arc seconds is not good enough for 3 millimeter observations. And that's why we encourage people to do offset pointing in closer. And then you're basically 1 arc second off potentially. But even 1 arc second is smearing out the beam, or 1 to 2 arc seconds is smearing your beam out a little bit. So we could potentially make some improvement there. And I would argue that our model is pretty good at correcting for the large scale gravitational distortions all over the sky, but we can probably do some improvement due to small track variations. We see that we have issues with the track now. In fact, the track's going to be shut down and have some concrete work done on it in the coming weeks. And also, we probably need to do a better job with the daytime thermal effects. And once we get LASSI up and going and trying to push LASSI into daytime observing, we will have to address this. Okay, the future.
You've got 3 minutes, Dave.
That's why we're having the meeting. Okay, and I'm basically done, almost. But I did want to bring up the point that, I mean, this would be an amazing instrument. It maps 10 times faster than Argus to reach the same levels, and which is also actually, it maps about 10 times faster than ALMA to reach extended source sensitivity. That's in our white paper. Gosh, that's a long link. You can look up the white page link from our web pages, as well as, but the thing that we haven't really highlighted, or a lot of people haven't taken advantage, even with the Argus, is we can actually map the CO transitions. Since CO is pretty bright on the sky everywhere, you need to look at star forming regions like 5, 10, 20 Kelvin on the sky. You do not have to go very deep. And you can basically map with Argus 144, 1 hour, you can map 1 square degree down to 0.2 Kelvin TA star, and that's with 1 km/second resolution. So in principle, we could really think big if we, and you could map hundreds to thousands of square degrees of star forming regions with CO with Argus 144 at unbelievable, resolution in the sense of the 6 to 7 arc seconds. So that would provide spectacular high resolution data cubes over large area of the sky to study, the environment in which the molecular clouds are forming and star formation is occurring. So I think that's pretty much all I have. So thank you very much. And I'll pop into it. Whoops, I can't see the Q&A.
I'll read the questions to you, Dave. So okay. First, big thanks to David. If you have questions, please put them in the Q&A and I will answer them online. You can ask them anonymously, but if you don't ask them anonymously, I still won't say your name. So it will be anonymous for the recording. If we don't get to questions, David is going to stick around and can answer them through the chat. So even if we don't get to your question, we'll still hopefully be able to get an answer. And David, one question I had is you mentioned the pointing improvements.
Yep.
Is the primary thing you need to improve the pointing hardware, or is it staff effort? Like
staff effort.
Staff effort, because you mentioned the track, and obviously concrete's expensive, but that's not the main thing.
Yeah, that part. But In the near term, it'll be analysis and staff effort. Well, this is a history. I mean, when the GBT was first built, the track wasn't sturdy enough to basically to maintain accurate pointing. So they made a much thicker steel plate, and that was replaced in 2007. And after that, the track variations, if you move the telescope around, the pointing, think of the telescope wobbling up and down a little bit, and when it you would only have like less than 1 arc second variations in that wobble. Over time, things have settled. Now we're getting 5 to 10 arc second variations as you move around in azimuth, and you need to model that. We need to measure that accurately and get that into the pointing model so we don't have significant variations. We can take it out in modeling. If we spent more time, we could do better job in taking out things in model, even if things start to, the foundation effectively sags over time. We could correct for that.
So we have one question, but I think I might save this for the LASI presentation. It's basically asking about the timeline and hurdles for the active surface rangefinder system. So LASI to eliminate the auto oofs. But I think that's probably, is that something that's going to be covered in the LASI presentation? I think it will be.
Yeah, I see. Well, sorry, we're not supposed to mention names. Somebody asked how stable are the side lobes measured for Argus 16. So they're not measured that often, in a sense. We should probably do some moon scans. I haven't done that yet. We have a significant air pattern, and depending on how you do your surface corrections, you can change your efficiencies. So the near side lobe patterns, I would argue, are probably pretty stable, but what's going out at some distance, there's quite a bit of power, or, at a half, like 30 arc minutes away, or like 10 arc minutes away. What's going on there, it's hard to measure. And so I can't answer necessarily how stable those are. I would suspect they would vary depending on how the surface corrections are done from night to night.
Thank you, Dave. So one last question, would you expect the track sag effect to get worse each winter with the freeze thaw cycle?
That's a good question. We should make some track measurements in the winter. What we do is we measure it before the start of high frequency season, and then we measure it at the end. And what you can see is, and then they do work on the track to replace a wear plate. And if you look at the data at the end of the season, you see these really tiny little variations, like these patterns as the telescope is going around, like in between track segments. You get these little deviations. They're not huge. And when they replace the wear plate, they remove that. But then over time, what we see from year to year is a sagging. So the whole pedestal, it's on a concrete cross, basically, that goes down to bedrock. So in between that cross, so that cross is very stable. It doesn't move. But what happens in between that cross of support, things can sag over time, and you see a general sagging of that over time, basically. Now, when they replace the track, they remove that, so they replace some of that concrete in between those main supports. So we'll in terms of the freeze, though, we should actually measure it. I think in terms of like the water table and stuff like that. We have very seasonal variations in our track parameters, so we haven't quantified that very well. But we will.
Thank you so much for that answer, Dave. But I'm going to have to move on to the next speaker. Sorry to cut you off.
No, you're not cutting off.
No, that's our next speaker. So if you could stop sharing.
Yes, see if I can get on here.
Yeah, so our next speaker can share.